Welcome back to Differential Calculus. In this video, we're going to look at some modeling with rates. I've talked about some of these basic ideas in previous videos, but I want to really focus on them here and see what we can do with that information and try to make some links to things that you've seen in the past. I'm going to specifically look at some kinematics ideas, some basic ideas in physics. If you aren't a student of physics, if you're not particularly familiar with physics, don't worry too much about it. I'm choosing this because I think that the examples are relatively straightforward, and that's going to go a long way towards trying to make the rest of this make sense. All right, but let's go ahead and construct a relatively simple mechanism. That mechanism is an object, a ball, which is anchored by a spring on other side. So the ball is freely able to move left and right across the floor. It is not going to move up or down, so we're in one-dimensional motion, which is important because right now we're doing calculus in just one dimension. Let's say that the position of this object is given as some function x of t. We're going to define x equals 0 as being right here at the center. X equals positive 1 is going to be the ball hits the wall on this side. X equals negative 1 is going to be the ball hits the wall over there on that side. And by some experimentation and some modeling, we figured out that the position x of t is given by cosine of 1/2 t. Right. The biggest confusion, the biggest place where students get mixed up in this is I have all of a sudden changed variables. Instead of talking about y as a function of x, that is no longer what's going on. I now have that x is some function of t. Right? So x is my dependent variable, t is my independent variable. And again, how I got the cosine 1/2 t, that's physics, that's not math. We're not worried about that. Our question in this course is, now that I know that, what can I do with that information? All right, so I'm not here trying to figure out how to write the model, how to write the physical interpretation, and how to use that to get a position function. I'm here to say what is going to happen afterwards. And I've mentioned this, I know, in previous videos, but I talk about position and velocity and acceleration a lot in this course because I think that they are relatively easy to understand. If your interests lie elsewhere, and I suspect for most of you, your interests will lie elsewhere and not in studying kinematics, because honestly, kinematics is kind of boring. But thinking about how some concept changes, how fast the measurement that you're looking at changes, the ideas of speed and velocity are going to work just as well in any other field. All right, so we have a position function, x of t is cosine of 1/2 t. And I know that velocity is the change in x over the change in time. Right? Velocity measures how fast your position changes over time. Or at least that's how we would phrase it in an algebra course. That's the average velocity. And that's the kind of thing of, you've driven down the highway, you've gotten 57 miles between your house and your destination. It took you 64 minutes. You can divide 57 miles divided by 64 minutes to get your rate of speed, your velocity. We are changing that now, and we are looking at dx dt, which is the instantaneous velocity. How fast are you going at this exact instant? And sticking with our more accustomed notation, we'll write that as x prime of t. So if x of t is cosine of 1/2 t, we can differentiate with respect to t. The derivative of cosine is the negative of sine, but I have to use the chain rule because there's a function, there's more than just t going on inside. So I just multiply this by the derivative of 1/2 t, which is 1/2. And now I have a function for the velocity. I can keep going in this style and figure out the acceleration, which is just the change in velocity over time. So that will be the second derivative, x double prime of t. Well, the derivative of sine is cosine. We again have to multiply by the derivative of the inside, which is 1/2. The negative stays out front. 1/2 times 1/2 is 1/4. And now we have cosine of 1/2 t. We could keep going down the list of all of those things if we wanted to, but position, velocity, and acceleration are usually good enough, so we'll stop with that. Here is a conceptually unrelated problem. The number of earthworms I spotted in my garden t hours after the rainfall can be modeled by the formula n of t equals 7t minus 1/2 t squared. And once again, I'm not worried about how did the model come to be. In this course, we are worried about, now that we have the model, what can we do with it? Figuring out how to use the model in the first place, or how to write that formula in the first place, is something for another course. In this case, probably a statistics course. But again, just we'll worry about what we can do once we have it, not how we got it for this semester. In this case, we're asking how fast were the earthworms coming out 3 hours after the rain? Well, the formula itself is giving me the number of earthworms. And we're asking in this question, how fast were the earthworms coming out? Which is not quite the same thing, but it's a related concept. It is, in what rate were the earthworms appearing? Well, mathematically, that's going to have to be n prime of t. This is a polynomial function. Taking its derivative is relatively straightforward. Derivative of 7t is just 7. The derivative of 1/2 t squared is just t. All right. We have that t is measured in hours. This problem is talking about 3 hours. So specifically, we are looking for n prime of 3, which is 7 minus 3, which is 4. All right, so numerically, we have our result. It is 4. I'm not entirely sure that that's useful. For what? Well, thinking about units, go back to the other notation for the derivative. Instead of calling this n prime of t, call it dn dt. That helps us remember. Well, we have here n is the number of earthworms. And t is hours. So number of earthworms divided by hours, we could interpret as 4 earthworms per hour. If it was linear, I would be able to divide that up further and say, oh, that's an earthworm every 15 minutes, but I don't think it's quite linear. And in fact, based on the formula here, it is definitely non-linear. So we'll leave it just at that. 4 earthworms per hour is how fast the earthworms are coming up at this particular moment in time. Right? When did the number of earthworms start shrinking? We'll be talking a lot more about this sort of a question a little bit later on in the course, but for right now, you know that the original model in this problem, n of t equals 7t minus 1/2 t squared, this is quadratic. Which means that the graph is going to be a parabola. The curve is going to look something kind of like that. And there is going to be a peak here in the middle. In a previous algebra class, you probably were taught a couple of rules that you could use to figure out where the peak was on a parabola. In fact, you may have even had me teaching you that in one of my other courses. And yes, those still work. There's nothing wrong with them. But in this course, I want to use that as a place to start exploring. Right? We know we could solve this particular problem using those tools that you are already familiar with. I want to use that fact to try to build some more general tools that will allow us to solve a broader range of problems. And in order to do that, I want to look at this a little bit more closely. In this figure, down here near the starting time, the number is growing very sharply. It's growing very quickly. The number of earthworms starts to slow down its change. And then it starts going the other way, slowly at first, but later very quickly. But the only way to go from going upward to going downward is somewhere in the middle to be going nowhere. In order for the number of earthworms to go from growing to shrinking, there has to be a place where the change in the number of earthworms is 0. And since we have a formula for n prime of t, we can rearrange quickly and get that the number of earthworms started shrinking after 7 hours. Again, I remember from the statement of the problem that t is measured in hours. So if the value of t is 7, that means that it was 7 hours. Sticking with the same scenario, I'm just going to copy it down again one more time for convenience. Another related problem: how fast were the earthworms leaving when there were only 20 earthworms left? All right. One thing I want to point out here is that there were actually 2 instances where there were 20 earthworms left. And one point, the number of earthworms was increasing, went beyond 20, and then the number of earthworms started decreasing, it fell back down to 20. So specifically, this problem calls out how fast were the earthworms leaving, so we know we're in that second case. Right? It's going to involve a little bit of algebra, a little bit of calculus, very similar to what we've been working on in this course or in today's video. But I'd like you to take a couple of minutes, play around with that, see where you end up with. And I'll see you in the next video.